Good morning. So my goal today is to introduce MerLin to you. I call it the PyTorch of quantum, and what we're going to discuss during the next 20 minutes is effectively how we improve the connections between quantum and AI. Maybe as a quick introduction, so as we go through MerLin, I just wanted to introduce myself. I'm the Chief Growth Officer of Quandela. I'm basically helping to make this company global. We have offices today in different countries, UK, Germany, Canada, Korea, and our goal is to expand on more than 70 countries in the upcoming years. We have more than 150 engineers, PhDs, across a variety of domains. And the last element is we're really building an ecosystem of partners to complement the capabilities and technologies of Quandela so we can scale our platform. So today, the subject effectively starts from what we deliver, which is a full-stack platform, where we have hardware, we design and deliver chips. We have an open platform called Pereira that really is the foundation for us to compute, to program, design our algorithm, and expose the capabilities across the cloud or on-prem platform. And we effectively have a cloud that allows us to expose a certain number of capabilities. I'll talk about the quantum toolbox in the cloud everywhere in the world. We've been the first company in Europe to expose the capabilities of our quantum computers in the cloud in 2023. So what's the goal today? I think once we establish at Quandela our full-stack platform, our next step was to provide application-native algorithm, what we call the Quandela toolbox. I mean, that's in quantum chemistry, for example, we have a primitive called variational quantum eigensolver, that methods that allow us to calculate the ground state of molecules. In optimizations, you may know CVAR-VQE variance, tailored for combinatorial problems. And in graph theory, we leverage the photonic native primitives like boson sampling, such as we can do a graph isomorphism or dumps subgraph identification. And that toolbox is really the first attempt for us to build a reality in the world of utility. So what does that mean? I think when we think about how we frame today's quantum opportunity, on the left, you have the NISQ era, the noisy devices with limited number of qubits. Usually we use it for proof of concept demonstration, toys demonstration. On the right, we talk about fault-tolerant quantum computers with large numbers of logical qubits and error corrections, what we call the quantum advantage here. But in between, that's a very interesting space, in fact, because it lies what we call the intermediate zone of utility that attempt to identify useful applications that already outperform the brute force. And the zone is not very static. It's expanding as new building blocks are added to our architecture. In Quandela's case, it's called SPOC, our spin photon optical quantum computing roadmap. And as we bring capabilities like deterministic entangled photons generation, spin photon interfaces, and feed-forward control, the power of the utility zone is expanding. So I can hear already the echo sometime of, yeah, but this middle ground is quite questionable. We can even argue on the definition sometime of the utility space. We hear a lot of skepticism. If it's simulable, it's no utility. I've heard noise kills any chance of advantage. Quantum is too slow to compete against GPUs. Without fault tolerance, there's no value. And I would agree that these concerns are very valid. There is no free lunch. Algorithms that makes use of this zone don't fall from the sky. They need to be defined. They need to be discovered, benchmarked, and refined. And that's all the purpose of MerLin, not as a magic shortcut to go to full core advantage, but really a framework for what I call systematic discovery. It allows us with the wider and AI quantum communities to experiment with new workflows where truly reality emerged. So let me pursue a little bit the introduction here. I think quantum machine learning is not a new idea. In fact, it has become the dominant theme in quantum application research, and we estimate that roughly half of all the papers on quantum applications are about QML. To illustrate this, our team looked at a large set of publications over the past years, and we found something very striking. First, nearly every QML paper uses MNIST as a benchmark dataset. And many of these papers are difficult, to be honest, to reproduce. Close half of them don't provide a code, and a significant number of them don't compare their results with classical methods. So while there is a lot of activity, there is also a lot of claims, some vague, some strong, and it's hard to make one's mind on what is truly progress and what is not. So the reality is that this activity really requires a much more structured approach, a framework that allows reproducibility, benchmarking, and systematic discovery, and that's what MerLin is designed for. So we want to effectively help the industry to benchmark, to reproduce, and discover new type of algorithm. So let's take a first concrete example that I want to share today from an early work we did with Airbus BMW in 2024 on quantum machine learning, and that was a challenge where we won the QML track. The task was generative learning problem and translating nighttime navigation images into daytime images and vice versa, a task relevant for a use case of autonomous driving. We explored two approaches. The first one was a fully quantum method called QGAN. And on paper, it looked very promising, very powerful, but in practice, the reality is that it didn't perform anywhere near to the state of art. So we turned to a second approach, which was very different. We started from a classical cycle GAN, which is the state of the art, and added a quantum annotation layer. And this layer is a boson sampler transformation of the image, providing the network with additional information. Here, the result was quite decisive. I think with this quantum annotation, the classical model performed beyond the start of the art. More importantly, we saw a strong reduction of hallucination. I think hallucinations appear effectively when in the case of translating images from day to night, we have the sunlight during the day, and you have building and traffic light during the night. So it creates false appearances of lights in the videos or the images that needs to be removed. So what's the conclusion here? I mean, for the first time, we had what we call the foundational insight. The value of quantum in the near term may not have replaced classical AI, but it really enhanced it with a new set of primitives that improved the outcome where classical definitely was struggling. And that's what we learned from this experience here, which is quantum can work very clearly alongside classical AI, bringing new primitives like boson sampling to improve the outcome. And this idea is reinforced by a second independent example that I'd like to share with you, the quantum reservoir paper. So here, you see some results from Sakurai, Hayashi, Monroe, and Nemoto's work at OIST, using a boson sampler as a quantum reservoir, exactly the kind of photonic hardware architecture we're developing at Quandela. The table summarized the test accuracies on three well-known datasets, DISC, K-MNIST, and FashionMNIST. What's very interesting just with this experimentation is with 3 photons and 32 modes, what we call the cork, effectively, already outperforms the linear baseline like LSVC across all datasets. And for MNIST, it reached nearly 98% accuracy, which is much better than a simple linear model and getting close to RBF kernel methods, which are strong but computationally very expensive. So on other dataset like K-MNIST or FashionMNIST,
Quark again beats the linear baseline and come close to the RBF kernel while using modest quantum resources. So the key takeaway here, again, is not that quantum already beats the best classical model everywhere, but that even with a small scale, quantum primitives expand the feature space in useful ways, giving hybrid system an edge. So that validated the idea that in a utility zone, with the right workflows, modest quantum devices can already enhance AI performance on meaningful tasks. So we're going to continue to explore this. To detail a bit more MerLin, it's really our first step towards a systematic framework for QML. It's designed to be accessible for AI researchers. No need to know quantum in detail with this platform. I would say step one, you can start anywhere on simulators, locally, or in the cloud, and validate ID's reproducibility. Step two, you can train at scale using GPUs, benchmark hybrid models systematically, just like in AI. And step three, when a workflow looks promising, you can deploy it directly on Quandela's photonics QPUs, and as Spock, like Pascal Sennelar before mentioned, advances bring entanglement and feed-forward, MerLin evolves with the hardware. So the goal for us is very simple. Make discovery of quantum-enhanced models reproducible, scalable, and hardware-ready. So what's the value proposition of MerLin? It's really designed to make QML accessible for AI researchers and enterprise teams. First, it's quite friendly. The interface feels exactly like PyTorch. You don't need to be a quantum physicist to try quantum layers. Secondly, it's scalable. We use GPUs to run large simulations and build a culture of benchmarking and reproducibility, just like what drove AI progress. And third, it's hardware ready. MerLin connects directly to Quandela's photonic QPUs via the cloud, and as Spock, as I mentioned, components come online, entanglement, spin photon interfaces, feed-forward. MerLin evolves with them. So that means that research center enterprises, they don't need to be upfront on the single case. They can explore systematically at scale and move to hardware when ready. So that's the value of MerLin, making QML accessible, scalable, and hardware ready. But how does it look like in practice? Let's look at a couple of examples of hybrid models you can build with MerLin. The first one is a very simple example, an hybrid classifier. You see a standard neural network with a quantum layer inserted in the middle. The structure is familiar to anyone who works with PyTorch, linear layers, activations, and now a quantum block. What's interesting in this quantum layer, this quantum layer doesn't replace the model. It adds a new degree of freedom. This means that we can capture and learn faster with fewer parameters or capture features that purely classical models might miss. That's a small control way to test if quantum primitives brings value. I'll show you a second one. This is an example that links quite to a previous case I mentioned, the Airbus BMW challenge. A classical model enriched with the quantum annotation layer. The quantum transformation provides extra features that improve the classification reliability. And once again, the important point, quantum doesn't replace the classical model, but it makes it stronger. Another one is, I think this one is a generative model, again, where the discriminator is hybrid quantum classical. This allows us to test whether quantum can bring an advantage in distinguishing real data from fake data, a core AI challenge. And again, the role of MerLin here is to let researchers try these experiments systematically and benchmark them. Finally, MerLin is designed to be cross-platform. Quantum layers can run on different types of hardware, photonic, gate-based, or hybrid. This flexibility is essential because each technology has strengths, and MerLin allows us to leverage them. So for enterprises, this means that they can explore QML today without being locked on one architecture. So that was basically a few examples that I wanted to share with you today. MerLin enables, as I say, hybrid model that combine the strength of AI and quantum. And the real value of MerLin is not in a single model. It's about being a systematic discovery engine for QML. So let's start to wrap up. I think if MerLin is our discovery engine for QML, it enables systematic, reproducible, and of hybrid exploration of hybrid models, scaling from simulators to GPUs to QPUs. It connects two communities, the vast AI ecosystem, more than 100,000 researchers, over millions of practicing data scientists, connected with now a smaller but fast-growing quantum community. And all of this serves one clear purpose: discover workflows where QML truly brings utility. So that is how we plan to move forward, not chasing hype, but building reproducible methods, tackling real use cases, and paving the way from today's NISQ devices to tomorrow's fault-tolerant quantum computers. So if you need to remember three things, I would say, first, Quandela is progressing along a clear roadmap from today's noisy devices to near-term utility to fault-tolerant quantum computers. Second, we already see concrete examples of quantum-enhancing AI workflows from our toolbox to Airbus, BMW, to independent results like Cork, I mentioned before. And third, MerLin is the framework that will let us scale this exploration systematically, connecting AI and quantum communities to find the real use cases where QML makes the difference. Quantum won't replace AI, it will empower it. And with MerLin, we're turning that vision into real use case. Thank you. We think it builds on our culture, creating value and powering breakthroughs. And we're really eager to share this with you moving forward.